All right, so today I would like to share with you 4 of my favorite problems. 3 of them are combinatorial related. First one, not as much. And before we continue with these 4 different problems, I have a warm-up question on the slides. And first, I want you to kind of think about doing mathematics and what feelings come to mind when you do mathematics. What are some of your feelings? Give me some words. Yeah. Discovery? Yeah. What are some other ones? Pain? Fun, yeah. So you get these opposite feelings. So you may say it's painful or challenging, frustrating, or you may say it's fun or joyous, or you may use the word ecstasy. The reason I'm using that word is because this problem on the slides here is in a discrete math textbook in the very first chapter, and it's titled The Agony and Ecstasy of Mathematics. And so this is a problem that's supposed to give you both feelings. So you're supposed to look at this problem, struggle with it for a little bit, and then once you actually reach this moment of insight and you can solve it, then you have the joy in mathematics. So one of the rules is don't tell others the answer. You should let them experience the joy themselves. All right, so hopefully this problem, once you actually solve it, brings a smile to your face. All right, continuing on, before we actually continue with combinatorics, I have a very important question, which is, what is mathematics? What do you think it is? And I thought long and hard about this question. It's actually when I went for my first academic job interview, this was the very first question they asked me, what is mathematics? And I think the following quote answers it best. This is a quote by the French mathematician Henri Poincaré. And he says that mathematics is the art, not science. Mathematics is the art of giving the same name to different things. And this quote really resonates with me because I do a lot of graph theory or the study of networks. And let me give you an example of that. So if you're working in other fields like chemistry or sociology or biology, you may come across different structures. So the chemistry example there is a hydrocarbon, and there's interaction shown between different carbon atoms. That interaction is a bond. And then in sociology, maybe you're looking at social networks, and you're looking at friendships between different individuals. And in biology, perhaps you're looking at what's called a PPI network, which is a protein-protein interaction network. And there's interaction between proteins, which are highlighted by a line between them. And as a mathematician, I look at these 3 things, and I notice they all have the same pattern, right? It's not a numerical pattern, like 1, 2, 4, 8, 16, what comes after 16? Not sure, but it's rather a structural pattern. And so when we do graph theory or networks, in mathematics, we study these structural patterns and the mathematical properties that they have. And then other people in these other fields can actually use that to make conclusions. So let's not talk too much about that, but let's continue with combinatorics. And combinatorics, a lot of you have seen it before, and most of you, if you've seen it before, would probably say it answers questions that are related to counting or enumeration. But there's actually 4 different questions that we have in combinatorics. And the first question is really an existence question. So proving the existence or non-existence of certain objects that have certain mathematical properties. This is a very important question, whether something exists. And I'll give you a quick example. So the question is there a group of 40 students at this campus, University of Toronto, Scarborough, who share the same birthday? So we're just looking at the month and the day, not the year. And the answer is either yes or no. How would you answer this question? What would you do? Would you go around and ask everyone for their birthday?
Are you saying this like people here or like this?
Not this room. But let's say look at all the undergrads who are on this campus.
So,
there's like maybe 15 or 16,000.
How would you say like you couldn't open people?
Oh, so you know some math already. So the comment was use a theorem that we teach our first year undergrads when they take a discrete math course. They learn the pigeonhole principle, and all you really need is that theorem along with how many students are here, and you can get the answer to be yes, and you can prove the answer is yes to this question. So you're not going to know who the students are, but you know that there exists a collection of 40 students. We're not going to do that today, but we teach that to our first years. Second type of problem in combinatorics is once you know that there is a solution to your problem, it would be helpful to create such a solution. So this is the construction problem. So here's an example. I'll give you a different example in words, but it's very useful when you're creating like a job schedule or your classroom schedule, or when we're scheduling our term tests for our students. You need some sort of method to do that. So this is a construction, and if you know stuff about networks and graph theory, it's a very well-known problem, and algorithms have been developed to solve these problems. The problem on the slides there is also quite famous, but it takes you into this other field called design theory, which we won't talk about today. All right, number 3 is what most people think when they see combinatorics. How many poker hands are there? How many ways can you make an ice cream cone with 5 different flavors of ice cream? Questions like that. And then the last one is also a big one application-wise. Once you know that you can create some sort of object with some sort of property, you want to do some sort of minimum or maximum. Okay, just being able to create it isn't important. You want to know, for example, if you were driving here today using GPS, you probably want the route that's the shortest time, right? So how does your GPS know what that is? What is the algorithm? And is it an efficient way to determine that? All right, so I gave you one problem already. Has anyone solved the one on the very title page? Yeah, 2 people? Okay, did you like it, or have you seen it before? Not too bad? All right, I gave it to my first year calculus students. This was a couple of weeks ago. Some of them are still working on it. But that's okay, that's okay. Once they solve it, they'll be happy. All right, this is my second favorite problem, which is quite combinatorial. And you may have played with these puzzles as a child. It's the 15 sliding puzzle, but you can have other configurations. It could be 3 by 3, right? It doesn't have to be this 4 by 4. And the 15 sliding puzzle is you basically slide these tiles into where the blank is, and you slide them around. And what you're trying to do is try to get like a picture. Maybe there's a picture of an elephant you're trying to create. This one here, you're trying to get the numbers from 1 to 15 in numerical order by sliding into the empty spots. So you want the one in the top left. So you want 1, 2, 3, 4 across the first row, 5, 6, 7, 8, and so on. So that's what you're trying to do. And in the late 1800s, this puzzle was incredibly popular because there is this puzzle maker, Sam Lloyd, and he created this puzzle, or claims to have created this puzzle, where all he did with the solved configuration from 1 to 15 was he took the tiles 14 and 15, and then he just swapped them. Okay, and then the question was, he asked the public, can you construct, so this is a question of construction, can you construct a sequence of moves to solve this puzzle? And if you could, you can let him know, write him a letter. They didn't have email back then, but you can go visit him, write him a letter. And he offered a $1,000 prize. I typed this into an inflation calculator, and it's about $23,000 today, if you could solve this puzzle. And I just wanted to read a quote from a book that Sam Lloyd writes about. So he writes about how he drove the entire world crazy, and so this was a big fad at the time. And he says that people became infatuated with the puzzle, And shopkeepers neglected to open their stores. Clergymen stood under a street lamp. They're trying to remember how they solved it. And the mysterious feature is that people who did solve it, they couldn't remember how they solved it. So you better write your moves down if you have a solution so you can share it. And then the last sentence is pilots are said to have wrecked their ships. And engineers, the people who drive the trains, rush the trains past stations. I don't think there's any shipwrecks because of this puzzle, people playing with this puzzle. This fellow, Sam Lloyd, he exaggerated quite a bit, and there's some quotes about him on Wikipedia. He was a bit of a hustler and not always truthful. And so when he actually gave this puzzle to the public, he already answered the first question in combinatorics, which is this question of existence. And this puzzle actually has no solution. You cannot go from the swapped 14-15 version to the numerical order. Now, it's not really clear why that is, but I'll show you in a few minutes with a smaller example to really demonstrate that. All right, if you have any questions, just let me know. Come on in, people, if you want. All right, so here are the 4 questions you would ask about this particular puzzle. So if you're training to be a mathematician, the first question you should ask is existence. Is there even a solution, right? And then only when you know that there is a solution would you actually bother trying to construct it. So the construction problem is give a sequence of moves that will solve the puzzle. And then once you know that you have a sequence of moves that solves the puzzle, you might want to count how many there are. This one is not too interesting because if you have one solution to the puzzle, you can kind of move the 12 back and forth between the blank to create longer solutions. And so if you had a solution, you'd have infinitely many. So what you really want is this optimized solution. You want the shortest sequence of moves that will solve the puzzle. So that's the actual goal. What is the shortest sequence of moves to solve the puzzle? And for the one that's on the slides here, there is none because there doesn't even exist a solution. All right, talking about optimization, I just want to do a brief detour. So in optimization, little games and puzzles like the sliding puzzle is quite useful in computer science because they can use these as a benchmark to test the efficiency of their algorithms and compare their algorithms to other algorithms for enumeration problems. So this is a simple puzzle with simple rules, and so it creates a great benchmark that you can use on your algorithms. So people have studied this in the literature, in math papers and research papers. And so questions about this optimization, how many moves does it take to solve the puzzle? This has been solved. So let me tell you that if you did start with the puzzle from 1 to 15 and you scrambled it, then you should be able to unscramble it and solve it because you can undo each move that you did. Right? So if you just started with the puzzle and scrambled it by sliding, then you will have a solution. And it was proven in 1999 that no matter how much you scramble it, you can do this 1,000 times, no matter how much you scramble this puzzle, you'll be able to restore it in numerical order in 80 moves or less. And there's examples of puzzles where you require all 80 moves, but most of them require less than 80 moves to restore. And then just to put that into context with the Rubik's Cube, by the way, there's exactly 17 starting configurations that require all 80 moves. But for the Rubik's Cube, this was also a well-studied object in terms of solving it. And so it was proven not too long ago that if you scramble the Rubik's Cube, you can actually restore it so that you have one color on each side and at most some number of moves. Does anyone know what this number of moves is? How many moves does it take, worst case scenario, to solve a Rubik's Cube? Or do you have a guess or an answer? 20, yeah. So it's actually proven to be 20. And actually, I think we have time. We can click on this link, and I'll show you a worst case scenario where you require all 20 moves. So this is called, I think it's some sort of superclip position. But it was in 2010 where they actually we're able to prove that you can solve every scrambling in 20 moves. So this scrambling is essentially, you take your cube and each of these edge pieces, you just flip them. So the green and white were flipped, and this red and green were flipped. And that's all they did with the Rubik's Cube, was flip all of these little side pieces. And then the moves that are allowed, you can do a quarter turn or a half turn, clockwise or counterclockwise. So this is one that takes exactly 20 moves to solve, and you can't solve it any faster. And you can see what's going on. Move it around. All right. Shall we wait for it to be solved?
Yes.
So that it's satisfying?
I think you should wait right up until it's solved and then just like
Rewind.
the last move that we go through. Just pause it right before the end.
No, that's cruel. All right, it has been solved. So that's the worst case scenario. That takes exactly 20 moves. Most of the algorithms that people use to solve Rubik's Cubes usually take, I don't know, 50 to 100 moves, right? Because maybe these moves aren't fast using your fingers. It might be better to do other things. Or maybe you don't know what the optimal solution is, but you have an approximate solution. All right, going back to the puzzle for the 15 sliding puzzle. So I told you that, so let me rewind here. I told you that this particular puzzle does not have a solution. You cannot, if you swap the 14 and 15 at the bottom, you cannot do these sliding moves to restore the puzzle in numerical order. And usually when you want to prove something like this, a very good mathematical strategy is you kind of start with something that's smaller. So instead of looking at 15 tiles, look at 3 tiles and see what happens. And this one you can actually make sense of by hand. So all I did was, I have this 3 sliding puzzle, I call it. So I have the tiles 1, 2, 3, and then the blank. And then I swapped the last 2. The 2 and the 3 have been swapped. And the corresponding question is, can you go from this configuration on the left to the configuration on the right? What is the sequence of moves that will do it? And then the second question is, suppose you're looking at this 1, 2, 3 blank puzzle and you scrambled it. What's the maximum number of moves that you might have to use to unscramble it? How would you compute that? So first thing is, you should know how many configurations there are, right? So how many possible theoretical configurations could this puzzle be in? What are the states that it could be? How do you figure that out? Yes?
We have 3 choices for the first place, 2 choices for the second place, and 1 choice for the last place, so 3 factorial.
So one comment was 3 factorial, which gives you 6. Not correct, but close. Yeah.
I think it's like there's 4 possible, like this is what empty space to be, and then you check like a 3 factorial for the arrangement of the 3 there are.
So what's your final answer?
So 4 times.
It would be 4 factorial.
And yeah, you have a different answer?
I think it's just 4, just because like.
Oh, there's more than 4. You can move the 2 down, that gives a different one. The 1 over.
Over, then 3 up, then that's just the rule. You can't perform any other thing because it just can't. Like,
Well, you'll see there's more than 4. It'll be convincing. I'll convince you. Yeah, do you have a different answer?
24.
24 is right, yeah. Basically, think of this blank as a 4. Put a tile labeled 4 there, right? And then there's this correspondence between the permutations of the numbers 1, 2, 3, 4, and these configurations. Every permutation of 1, 2, 3, 4 gives you a configuration. So 1, 2, 3, 4 is exactly the one on the top right. 1, 2, 3, 4. But if you move the 4 up, or rather if you move the 2 down, you're just switching the 2 and 4 tile. So you'll have a 1, 4, 3, 2, which shows up somewhere. Oh, right here, 1, 4, 3, 2. And then this is what you would say is the permutation 1, 3, 2, 4. Okay, so there are 24. And in my research area, one of the things I study is something called a reconfiguration graph. And you can draw these reconfiguration graphs for different types of problems. So usually I do it for graph coloring problems and other problems in my field. But what you want to do is essentially figure out what are the states of your system and how can you move between the different states. So let's draw this reconfiguration graph. How can you reconfigure the puzzle into other configurations? So let's suppose we started with the 1, 2, 3 blank state. This is what you can say is the solution. That's what you're trying to get in your puzzle. What are the possible moves that you can do? Well, there's only 2 possible moves. You move the 2 down, or you move the 3 over. And so those are 2 brand new states. And what I'm going to do is I'm going to connect 2 states with a line if you can go from one to the other. And then from the 1 blank 3, 2, you can continue moving things clockwise. So you can move the 3 over, the 2 down, the 1 over, and what you get is moving the 1 over, you get this state. There's nothing else you can do from this 1 blank 3, 2. Either you move the 2 up and you go back to the original, or you move the 1 over and you go down to this next one. Okay, so if you start repeating this, going clockwise around the circle is rotating these pieces clockwise, and counterclockwise is the other one. You can see that you get these kinds of configurations, and they actually converge on 1. So they actually converge on this blank 3, 1, 2, and then you're kind of stuck in this cycle. So you can rotate the pieces clockwise, and you'll hit all of these configurations here, but that's only 12 configurations. There's a whole bunch that are missing, that you can't actually scramble 1, 2, 3 blank. You can't scramble it to get the other configurations. So the other ones happen to correspond to where the 2 and the 3 are swapped. So if you start with 1, 3, 2 and start rotating your pieces, it also forms this nice ring or cycle of configurations where you can go from any of these configurations on the ring to any other configuration. And this solves the problem, right? It tells you that you cannot go from 1, 3, 2 blank all the way to 1, 2, 3. That is impossible because there's no line that you can travel along to get there. It also solves the optimization problem. The worst case scenario, if you did have a solution for 1, 2, 3, a scrambling of it, the worst case scenario is this opposite one, which actually requires 1, 2, 3, 4, 5, 6 moves, right? So you're looking at what's called the diameter of this graph, and that's the worst case scenario. So that's what people did for the Rubik's Cube. You can draw this kind of picture, and people did this for the 15 sliding puzzle as well. These pictures are a little bit more complicated, but this pattern arises. So if you did this for the 15 sliding puzzle, then you have how many states are there? 16 factorial, which is about 21 trillion configurations. So I'm not going to draw it for you. I don't think I could. But there will be 21 trillion configurations for the 15 sliding puzzle, but it breaks up into these 2 components, where from this numerical state, you can reach exactly half of the configurations, and when you swap the 14, 15, you can reach the other half. All right, so that's a little bit of insight how you might approach these problems and solve it using something I use in my research, reconfiguration graphs. All right, let's continue. That's my second problem. So I said I would share 4 problems with you. So this is the third problem, which has a very nice combinatorial solution. You can consider this a combinatorial geometry problem. And what you do is you take a circle and you put endpoints around the circle and you connect all of these endpoints with straight lines. When there's only one point on the circle, there's nothing to do. You just have that single point. And the question is, when you apply this procedure, so let's say you did 2 points, connect them with the line. When you apply this procedure for endpoints, what's the most number of regions that can be formed? Or if you put this rule in that you can't have 3 lines intersecting in a single interior point, then you're already at the maximum number of regions you can form. So with that extra rule, you're just asking how many regions are being formed. So let's do some counting, see if we can find a pattern. So for 3 points, it splits the circle up into 4 regions. For 4 points, add another point, draw the lines to the remaining 3 points. And how many regions do you get? So you have to draw it, do some counting. I've already done that for you. All I did was add this extra point, and I got 8 regions, right? What do you think the next one is? 16? What is your reasoning for that? Is there a reason why you...
No, by the check drawing.
Just guessing? Guess and check. Very good strategy. It is 16. So I just added another point. What's the next one after that?
31.
32, 31. People who have seen this before are not saying 32. They don't want to get tricked. If you're saying 32, you have to actually justify why is it doubling? Is there a reason for it to double? And the answer is no. There's no reason for it to double. The fact that it's doubling right now at the beginning of the sequence is just a coincidence with the actual formula. So if you thought it was going to double, your formula would be 2 to the number of points minus 1, right? So to get the number of points, if that's n, you do n minus 1, and you do 2 to that power. 2 to the 1, 2 to the 2, 2 to the 3. But yeah, this one is 31. And I'll prove it to you by counting, right? You can just label all of the regions, and you'll see that you don't get 32 regions. So this is a lesson to you to be careful when you're generalizing patterns, because it may not always be true. And that makes all of these like IQ tests where you have to guess the next number and stuff. It's more like you have to guess the pattern that the person who wrote the question is thinking of. So whoever wrote the question has a particular pattern in mind, and it's can you guess this pattern or not? So here the answer is 31. What is a nice formula for it? Well, we're not going to go through it in detail. It does have a lot of combinatorics in it if you do it that way. But the formula is, if you write it combinatorially, we use binomial coefficients to write it. But you can expand this into a polynomial of degree 4. So if you have n equals 1 point, and you plug that in, you'll get the answer for 1. And if you plug in n equals 2, this polynomial will output 2, and so on. Okay? And then if you're stuck on a sequence, there's this very nice encyclopedia, or database of sequences. It's called the Online Encyclopedia of Integer Sequences. And if you're trying to figure out what is the next term in the sequence, this will tell you possible answers to your question. So let's say I started giving you 1, 1, 2, 3, 5, and then I gave you 8, and then say 13, and then say 21. You might say, well, I don't know what the pattern is. Some of you can see what I'm kind of trying to do, but just ask the computer. And the most popular continuation of the sequence is you're basically adding the previous 2 terms together. So you'll do 21 plus 13 to get the next one. So this is a very famous sequence, the Fibonacci numbers. And in this encyclopedia, it takes up a lot of space until you can actually get to the next sequence, because it's so popular. The next sequence doesn't take up as much space, but another continuation is this one here. So those are possible sequences that you could be describing. Without more information, though, you don't really know. So that's a little lesson about sequences. All right, that was my third favorite problem. The last problem, I want to be a little bit interactive with you, and so this is more of a game. It's in combinatorial game theory, and I usually do this with so sometimes I teach Introduction to Combinatorics, which is a third-year undergrad course. And so sometimes I'll have them try to figure out strategies for this game called NIM. And it's a combinatorial game. It has a lot of mathematics in it. And so let me kind of give you an overview first of combinatorial game theory. So you're thinking of games that are 2-player games. There's no luck or chance involved. And both players have perfect information. So a game like tic-tac-toe would be somewhat combinatorial. And some of the games that you play, you may think that you can't win because there's no strategy you can use to guarantee a win. And so we say that a player has a winning strategy if they can guarantee a win no matter how the other player plays, But a lot of the games that you play, they usually end in a draw. So games like tic-tac-toe, if you know what you're doing and you know how to play, you can't lose, right? You can always guarantee a draw for yourself if you know what you're doing, right? And you have to play efficiently. So a game like tic-tac-toe, if your opponent is playing perfectly and you're playing perfectly, it'll end in a draw. All right, let's do a more difficult game. I want to talk a little bit about this game of checkers. So this is also a game that's been mathematically solved. And it was actually solved in 2007 by a team of Canadian mathematicians and computer scientists. Go Canada. And it was solved by Professor Jonathan Schleifer. So he actually did his bachelor's degree here at the University of Toronto. Right now he's leading an artificial intelligence group at the University of Alberta. And so I just want to share this quote with you from Wikipedia. So it says that he solved this game of checkers in 2007, right? So it says in 2007, after 18 years of computation, so he did a lot of computer simulations and stuff like that, he was able to prove that checkers always results in, and then the options are the following. Whoever moves first, maybe they have a strategy where they can win no matter what, or maybe it's the person who moves second who can win no matter what, or maybe it results in a draw. What do you think the answer is for checkers? Do you think the person who plays first has an edge and they can guarantee a win? Or do you think it's like tic-tac-toe, a very boring, is tic-tac-toe boring? Oh, okay. A very not boring game, which mostly ends in a draw, right? Checkers is the same, right? If both players play perfectly and they don't make mistakes, it'll end in a draw. So he was able to prove this after a lot of computation, looking at the different states that the board could be in. All right, one more game before we get to the main one. Connect 4. Lots of you have played Connect 4. There's a little animation on Wikipedia that I will show you. And the idea is you have these tokens. So there's a player 1 and a player 2. Yellow looks like they're going first. I think they go down the middle first, right? Let's repeat it. Yeah, so yellow went first in the middle here. And they take turns dropping the tokens into this grid of 7 by 6. And you're trying to get 4 in a row. Has anyone not played Connect 4? Oh, you haven't? 2 people? Okay. So this is the game. It's much easier to analyze than checkers. So this was actually solved a little bit earlier. So what did we say checkers was? 2007. So when do you think this game was mathematically solved? Case analysis of all possible positions. Not as difficult as checkers. It was solved in 1988. And what they proved is the following. So we have to see, is this game also going to end in a draw? Can you guarantee to tie the game if you go first? Or do you have a strategy you can use to win? So what's your intuition? If both sides play perfectly, and you know how to play, your opponent knows how to play, can you force a draw? Can you win? What do you think? What's your guess?
Like, then when you don't play perfectly, it's always a draw.
Oh, really, really? Well, what they proved though is if you play first, you can win. But you have to know the strategy. So that's what they proved. I don't know if anyone knows the strategy. It's pages and pages and pages of mathematics, what you do. But what you have to basically, your next move depends on what your opponent does, right? So it's not like a simple strategy where you just always play in the middle. It's based on what your opponent does, this is what you do next. Okay, so if you know this strategy and you play first, you can win. However, you have to play in the middle as the first player, because if you play on the first or last column, then they showed that there's a strategy the second player can use to win. And if you play in the second column or the third column or the fifth column or the sixth column, they showed that that game will end in a draw afterwards. Okay, so if you want to win, the winning move at the beginning, go in the middle, or play against a child who doesn't know what they're doing, and then maybe you can win. But go in the middle first, and then from there on, it depends on the opponent. Okay, so to guarantee a win, that's the first move, and then the rest of your strategy depends on your opponent's moves. All right, any questions before we move to my last problem? Yes?
Has somebody set up one of those websites where you can try to play Connect 4 against the perfect AI and lose every time?
Question was, has anyone set up a website where you can lose every time? And probably. I don't think, it's probably like a nice homework question you give to some undergrad. Program Connect 4 so that the AI plays perfectly. And it's just a bunch of casework. I'm sure the people who solved the problem did exactly that. And they can just use the code that they have to play perfectly. All right, here's the problem with a nice combinatorial solution. Looks like we have a few minutes to discuss it. So this is the game of NIM. And the goal is essentially you have several piles of these look like little candies. And say you had 4 piles of sizes 2, 1, 5, and 3. Well, the object of the game is to take essentially the last candy from the table. And the rules are you can select any pile and then pick you can take any number of candies from that pile. So for example, your first move might be select the 3rd pile and take 1 candy from it. And then the second player might take 3 candies from the green pile. You could take anywhere between 1 candy and the entire pile. And you go back and forth, and the winner is the player who basically clears the table. It's not who has the most candy, but whoever clears the table, takes like the last pile or the last candy, is the winner of the game. So let's play this game. You can stick around. This is all I have prepared, but I want you to think about this game while we play it. And I want you to think about, first of all, let's do one. One pile is not fun, because if you only had 1 pile of candy based on the rules of the game, the first player could take the entire pile, right? So for 1 pile, not that interesting. First player always can win by taking the entire pile. So this is the one that I want you to think about. So 2 pile NIM, so piles of sizes 3 and 5, and size 5 and 5. Who can guarantee a win, player 1 or player 2 in the first game? Who can guarantee a win in the second game? And this involves a little bit of mathematical thought. And if you do have an answer, what is one word to describe your winning strategy in a sense? All right, so I have some candy for you to play the game. It looks like these little candies. Do you like Starburst? So I bought a bunch of Starburst so we can actually play the game. Anyone want to help hand Starburst candy out? And you can have Starburst. Let's give everyone a Starburst.
I guess I can hand these and then people will hand them out.
I'll just give 1 each. Everyone, yeah.
No, and then people
Oh,
can
you
hand them
want?
out.
Oh, thank you. All right, if the rules don't make sense, let me know. I'll walk around and I can clarify any of the rules. But yeah, try it with a friend, try it with yourself. And if you have a strategy, let me know.
Number of